So the opening session is by Jesper Møller from the University of Copenhagen, and he's talking about equivariant Euler characteristics. Please.
Yes, thank you. Thank you. So first of all, I would like to thank all the organizers behind this conference who have been working tirelessly for weeks and months and years to prepare this event. It's just a shame that so few people can be able to attend in person. Okay, so I'm going to say a few words about the equivariant Euler characteristics, and they are invariants, integer invariants of group actions. So I'm going to give the definition first. To motivate the definition, let me remind you about some combinatorics. So in the first case, suppose you have here M is a set, and it's a set with a group action. So everything you will see from now on and the next 60 minutes will be finite. So do infinite things exist at all? I'm in doubt. So everything will be finite. So here's a set with a group action. Then there's a formula for counting the number of orbits for this action. And the formula goes like this. So you take, let me say, you take the number. Let me write it first, and let me then say that this stands for the points in M fixed by G. So the number of orbits is the average number of points in M fixed by the elements of G. So this is often known as the lemma not due to Burnside. That pretty much specifies the lemma. So here M is just a set with a group action. Now let's take M to be something. Something could be a set, but it could also be other things, as long as these other things have Euler characteristics. So now M is something with an Euler characteristic and with a group action. Then it's actually the same formula. So this formula here computes the Euler characteristic of the orbit space, or what it is, the quotient here. It's actually the same formula. So this is the average number of Euler characteristics of the fixed points sub-objects. And this is often, the name Lifshitz is often attached to this lemma here, but they are actually the same statement. So I would say this is not Lifshitz nor Burnside's lemma. Okay. So these formulas here, they count, for instance, the Euler characteristic of the quotient set or CW complex, or what it can be, compact manifold. Okay, so let me write this formula here in a slightly different way. It's the same formula, but I reformulate it. So I say instead, we take a sum Euler characteristics of things fixed by X, where X, well, I should run through the elements of G, but now I say I let X run through all homomorphisms from an infinite abelian group to G. So it's the same formula. I have written the same thing twice. So let's assume that that we are Sir Michael or Graham-Segal. And suppose we are in the same situation. So we have something with an Euler characteristic and with a G action. So if we are brave enough, we are going to take this formula here, but replace the homomorphisms above by homomorphisms of an infinite. Oh, did I say everything was finite? Okay, so an infinite abelian group on R generators. So now X runs through all these homomorphisms, and we take the Euler characteristic of the points in M fixed by these homomorphisms. So for R, if R is 1, we are back to the old formula. But we have now a number for every R. And this is the R equivariant Euler characteristic. So it's a sequence of numbers associated to this group action. So here are some special cases. So is this visible? Yeah. I equals 1. Well, we designed it so that the first equivariant Euler characteristic, that is the usual Euler characteristic of the quotient. If the group is trivial, so if G is equal to 1, there are not that many homomorphisms here. And we get just, so for all R, the R equivariant Euler characteristic is just the usual Euler characteristic of M. This is a 1. And if the set we're acting on is a 1-point set, yeah, there are plenty of homomorphisms here, but there are not so many possibilities for the fixed point set. So what we get is 1G is 1 divided by, it's the number of homomorphisms C to the R to G divided by the order of G. So that's the equivariant Euler characteristic of 1 point with a group action. Yeah, I should say also that this number here, it's an Euler characteristic, so it's an integer, and it will follow inductively that all these numbers here, they will also be integers. Yeah, so that's a definition. Yeah, so let me also say, because this will be relevant later, that is, maybe I will write here then. Is it okay to write here? Yeah, okay. So let me say that if this thing that we are acting on is equivariantly contractible, then the equivariant Euler characteristics will bring us back to this case here, because M is up to homotopy a point. So if you have something contractible, the equivariant Euler characteristics are going to be the numbers we have there. Okay, so that's a definition. So you could say it's motivated by these old formulas here. It was not the way that Atiyah and Siegel motivated the definition. They came to this definition via string theory in physics. And don't ask me how. So here's some classical formulas for equivariant Euler characteristics. So they go back to a time where equivariant Euler characteristics were not defined at all. But that did not prevent Stanley for computing them. So if you take so I take the equivariant Euler characteristic of one point with an action of the symmetric group. So that means that I compute, the number of homomorphisms may be divided by n factorial. And also this number of homomorphisms means the number of points in G are sequences of points in G that commute. So this means the number of R sequences in the symmetric group where all the elements commute. So if we can express that number in terms of infinite product expansion. So it goes like this. So this is the infinite product expansion. And the thing here is the number of subgroups of Z to the R of index K. Okay. Yeah, yes. So let me just. Yeah, right. Yeah. Yeah. Thank you. Yes. So that gives a number of commuting R tuples of elements in the symmetric group. And then later on, these people here who knew about equivariant Euler characteristics generalized this formula in this direction here. So now we take, let's say M is a manifold, compact manifold with a G action. We take n copies of that, and then we have an action of the wreath product on that manifold. It's a G manifold, but we have n copies, so we have permutation action. And these Euler characteristics, they are, we take the generating function just computed by Stanley, and then we raise to the power of the arc equivariant Euler characteristic of M. So that's you could say that's a generalized version of Stanley's formula. In Stanley's formula, the manifold M is 1 point with no G action, with action of the trivial group. And if we take R equals 1, so we are computing the Euler characteristic of the quotient, then this formula here says that the Euler characteristic of Yeah, so we should take m to the power n, and then we should take the quotient by this group. So we get the symmetric n-fold product of m mod g. Right, this is the quotient. So we take r equals 1. So we are computing the Euler characteristic of the quotient space here, the set of orbits. And yeah, let's say we take the g action first, then we have n copies of m mod g, and then we take the sigma n action, so we get the symmetric product.
Jesper, there's a question in the chat.
Yeah.
If there should be an x to the n in the right-hand side of the last formula.
Yes, where in this formula? Yes, 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 yes. Absolutely right. Yes. Okay. So what is this going to be? So it's going to be 1 minus x. So I apply this formula here. One minus x to the power of minus g. So and that's the oldest version of formulas like this. So we will pretty soon need some variations of the equivariant Euler characteristic. And the variations we're going to use is, first we're going to use a reduced version. So we will speak about reduced equivariant Euler characteristic. And that is the number you get by taking here in the definition, you take reduced Euler characteristic everywhere. That will also be the non-reduced Euler characteristic minus the Euler characteristic of a point. And the thing here is that if now m is g contractible, maybe I should say 1. Yeah, then the non-reduced Euler characteristic is this number here, but we subtracted that number. So the reduced Euler characteristic is going to be 0, all of them. So the reduced Euler characteristics of something contractible, G contractible, they are all 0. So that's a reduced version. We're also going to use a, what could be called a P primary version. P is a prime. So there are P primary, and now I take reduced equivariant Euler characteristics defined by the same formula as here, except we take another group here. And the group we will take is, yeah, so it becomes the right thing to take is this group. So this is the integers, and this is the p-adic integers to the power r minus 1. And then you take, yeah, the same thing as before, the reduced Euler characteristic of the points fixed by these homomorphisms. So the point about this P primary equivariant Euler characteristic is that it can be, what is it that you say? So it can be categorified. Yeah, that's a p-adix. Yeah. So you take sequences of R elements in G. The first element of the sequence can have any order, but the remaining elements of the sequence must have order a power of P. So most of the time you only see P elements in the group G. And the good thing about this P primary invariant, and that's, okay. So Hopkins, Boone, Smith, Taminoy, they show that this number here, here it's defined in a combinatorial way, but it is an Euler characteristic as we know it. So this P primary Euler characteristic of Mg is the Euler characteristic computed in Morava Arth K-theory at P of the homotopy orbit space. So in this way, yeah, there's a connection to topology here. These numbers, they are actually Euler characteristics of a space. Yeah, so that was a definition, and these were some early results, and these were some variations. Now I would like to focus on a special situation where we have something with a group action. Something we have seen before. So, so I would like to take the P subgroup poset of a group. So S, G, P, the poset of P subgroups of G, finite group G, ordered by inclusion. So it's partially ordered set, and there's the group G acts by conjugation on its subgroups. I take non-trivial P subgroups. Otherwise, it will be contractible. Yeah, and here I would like to mention two conjectures. Yeah, so we have, in this situation, we have these reduced or non-reduced Euler characteristics of this poset with this group action. So the first thing I would like to mention is Webb's theorem. So he computes, yeah, the way he said it is that you take the P subgroup complex and the orbit space, and this has Euler characteristic, reduced Euler characteristic 0. Okay, so when we see something that has reduced Euler characteristic 0, we say, it must be contractible. That's the way we work. And this is true. Yeah, so this is Simon theorem, that this, you take this poset, or you realize it, and then you take the orbit space, and the orbit space is contractible. So in this situation, at least, the equivariant Euler characteristics, they indicated that we were staring at a contractible space, and this is true. So it's true for groups, and this is the original result, but it's also true for fusion systems. Then you of course have to interpret what this means. Yeah. So when I write this, I should say you realize it and then you take the quotient. Yes.
If there's questions from the audience, could you repeat it, because otherwise we cannot hear the question. That would be helpful.
Oh. Yeah. So the question was, what does a simple like this, what does it mean? And the answer is that it means you first realize this partially ordered set. So now we have a topological space, and then you take the space of orbits. Yeah, so that's Simon's theorem, and its generalizations to fusion systems. We will not need that here. Okay, so let me mention the first conjecture. And I should say right away, I have no idea how to prove this conjecture. So you could ask yourself, what happens if we take the second reduced Euler characteristic of this P subgroup complex? Oh, sorry. Can we go back on the computer 5 minutes? Because I want to use S here. So we're talking about S subgroups. Because I used already the P for primary Euler characteristic. So there's no P now. There's just an S, and we're talking about S subgroups. Sorry about that. Because we want to use P for primary Euler characteristics. So we take, you could ask yourself, if you have nothing else to do. So we take the second equivariant Euler characteristic of the S subgroup complex. And to that, we add a number. So we add the number of irreducible complex representation of this group. That's seen from the prime S as maximal dimension. So the dimension should be maximal seen from the prime S. So I take the dimension of the representation, and then I take the S part, the highest power S that divides this number. Yeah, so you could ask yourself, if you add these two numbers, what do you get? Okay, very good. Yeah. Okay, so we are looking at this at this poset of S subgroups of a fixed group, and it has a group action by conjugation. And I would like to mention two conjectures. So the first conjecture is this Robinson conjecture, that this number plus this number for all cases will give 0. And it's possible to do, I mean, you can take your favorite group if it's not too large, and you can actually, with the computer, you can compute these two numbers, and they add up to 0. Okay. The second conjecture, so that's Robinson conjecture. The second conjecture I would like to mention is a Quillen conjecture. It's known in many, many cases, but it's not known in full generality. So let me state it this way here, that on the right side, I have 3 statements, and they are equivalent. So I actually repeat the same statement 3 times. So those 3 statements are that the subgroup complex, the S subgroup complex, is G contractible. That's actually the same thing as saying that it has a G fixed point. And that is actually the same thing as saying that in purely group theoretical terms, that G has a non-trivial normal S subgroup. So this poset has some special properties. I mean, it's not usually the same that just because you have a G fixed point that your poset is G contractible. But that is the case here. So the Quillen conjecture asks for a sufficient condition, a condition that they will imply block A here. And Quillen himself, he said, could it be that if we say that the S subgroup complex is contractible? Could that be sufficient to conclude that it is actually G contractible? A little more bravely, so we agreed that whenever we see something with reduced Euler characteristic 0, it's contractible. So a more brave conjecture says that if the Euler characteristic, the usual Euler characteristic, thinks that this poset is contractible, then we can actually conclude block A. So that's a stronger conjecture. And a third variation, so you could use these reduced Euler characteristics, reduced equivariant Euler characteristics, and you could assume that the equivariant Euler characteristics, all of them, they think that this is G contractible. Then you could ask, is this sufficient to conclude block A? So these are 3 variations of Quillen's conjecture. And as I said, known in many, many cases. Okay, so that brings me to the next part. And in the next part, I just wondered, what are these equivariant Euler characteristics for some concrete groups? So I don't know what number, section 4 maybe. So the equivariant Euler characteristics of these subgroup complexes where G is a finite group of Lie type. And so finite groups of Lie type in characteristic Q where Q is a power of S. And the cases I looked at, they are the general linear group, the unitary group, so that's so this, yeah, so it's well, never mind. So that's a subgroup. That's a subgroup that preserves in bilinear form, that is Hermitian, symplectic group, and you could say orthogonal groups, various types of orthogonal groups. So I was just curious, what are the equivariant Euler characteristics in these cases? So I know the answer in this case, in this case, in this case, and you have to do it in this order here. You have to do it in this order here because, yeah, it has something to do with so you can compute the equivariant Euler characteristic recursively if you know something about centralizers of elements. And all centralizers of sufficiently nice elements here, they will be in this general linear group, they will be general linear groups. All centralizers here, they will be of this form or of this form. All centralizers here will be of this form, this form, and this one. So you can work yourself down this list here. So when I came to the orthogonal groups, I ran out of steam, but I think you can do them. So you use a recursive approach. Yeah, and let me tell you what you get in this case here, when you have the general linear group. So you take the S subgroup complex GLN FQ. Q is a power of S. And now I remember the X to the N. So this is going to be, I'm going to write it in two ways. So you can write it as a product, R+1 factors, 1 minus Qj times X raised to a power that is a binomial coefficient with a sign. And you can also write this as exponential function applied to minus Q to the N minus 1 raised to the power R times X N divided by N. Yeah, and let me also say that's going to be on another. So these are the equivariant Euler characteristics. So if you are interested in the P primary part, Yeah, so this more topologically inclined version, then you can use the same formula. Well, except that you take the p part of this number here. So now I have both a p and then s. Yeah, so what should I say about this? I should say that so we are maybe especially interested in the second equivariant Euler characteristic. Yeah, this conjecture turns out to be true. So if you take the second reduced equivariant Euler characteristic, what you get is what is minus 1 minus q x. And yeah, if you remember your Taylor expansions and things like that, you will see this is constant coefficients. So these equivariant second Euler characteristics, they are all 1 minus q. And this number here of irreducible representations, in this case, G is GLN FQ, that is Q minus 1. So these two numbers, if you add them, I think you will get 0 in that neighborhood. Yeah. So I should say maybe a few comments about this this p primary situation here. I should say, yeah, so I should say that if p equals s, so we're taking the subgroup S subgroup complex, and we're also taking S primary equivariant Euler characteristics. So if this number here is a power of S, and we subtract 1 and we take the S part, there's not so much left. This will never be divisible by S. So this will be a 1. So what you get out in that case is that these Euler characteristics, P primary Euler characteristics, they are most of the time, so for n greater than or equal to 2, you get a 0. So all the equivariant Euler characteristics. Yeah, so, and since the equivariant Euler characteristics, they are Euler characteristics of a certain space, a homotopy orbit space, it sort of indicates that we are looking here at the homotopy orbit space that is contractible. I don't know if that is true. Also, I should say that if we take the S subgroup complex but compute the equivariant Euler characteristics, P primary at a prime P different from S, the numbers you get So this generating function here depends only on, yeah, something some of you have seen before. So these numbers here, they depend only on, so P and Q are different prime powers. So I take the subgroup generated by Q inside the group of units in P at X, and I take the closure of that subgroup. And you could, so that's one way of saying it. You can also say it in terms of number theoretic functions. So this number P primary Euler characteristics depend only on this number here. Just as the fusion system. Yeah. So I will not say that the equivariant Euler characteristics are functions of the fusion system, because that would be stretching it too much. But now I said it anyway. Yeah. So there are different other ways of expressing these generating functions here. Yeah, and they show some. Yeah, okay. So maybe I could say. So here's one consequence of these numbers. So this is something that comes out of the computation of these equivariant Euler characteristics. So that is polynomial identity. For partitions. And the first place I have seen something like that is in some papers by Tevenats. So we are going to talk about partitions. So here is the natural number. Here is a partition of that natural number. So a partition, what is that? That's a multiset. So you have some natural numbers B1 and B2, and you repeat B1, E1 times. And this is a partition of N if E1, B1 plus E2, E2 equals N. And this, I say this is a base of the partition that consists of these numbers B1 and B2. And I say the exponent of in lambda of B1 is E1. So what do you get? If you take this sum here, n greater than or equal to 1, so you take now all partitions of n. Whenever you have a partition, you go through the elements in the base. And for the elements in the base, you take the number of irreducible, what do we say when you have two polynomials and you cannot factor them? Irreducible polynomial, if there's no factorization. Irreducible. Yeah, they are called irreducible polynomials. You cannot factor them into two. Yeah, irreducible monic polynomials of degree b in the field with q elements. The number of irreducible monic polynomials of this degree in this field with q elements times m. M is some number minus the exponent in the partition of that number times xm. So you make this huge function here, generating function, and what do you get? You get 1 minus qx, 1 minus x to the power m, and m, yeah, m can be any rational number. So that's an identity for, yeah, it's a polynomial identity for partitions, integer partitions. And it is hidden somehow in this general linear group. So this is the identity you get for the general linear group. Hidden inside the other groups are similar identities. Yes, I think I will stop here.
Thank you. Let's see if there are any questions or comments. First, with the people inside in the room. Are there questions? Remote questions?
Can I ask a question about that function, the x, the thing that's on the screen at the moment? Does that happen to be it looks a bit like a zeta function or something like that? Is it? No, on the other board. This one up a little bit, the bottom of the board.
So what's
bottom
on
of the top board?
Repeat the question, please.
I can't.
So that's that screen. You mean
up?
You mean here? Is that
up?
Up. Okay. Yes.
Yeah.
So this function here.
Yeah.
Yeah. Okay. So and what is the question?
Is it a zeta function?
Yeah. I think it is. In some cases, it is a zeta function. Yes. In some cases, it is. But I don't know why it is a zeta function. I just know that they happen to be zeta functions. Yeah.
Okay.
It's true. Yeah. So it can. This number here can be expressed in another way, using other versions of this function here. So you could have other versions of this. Some like. Where the power are, so this function here you could say is the first layer of a function, but there's a whole sequence of functions, one for each r, and yeah, they can also be used to express this number here. So yeah, this is a number. This is a number. No, this is a number. No, I should say this is a generating function. This is a generating function with coefficients in a field of polynomials. So there's a difference between the two objects.
So I wanted to ask if some parts of all this make sense with compact Lie groups instead of finite groups.
Probably, yes, probably. Yeah, so it does make some kind of sense to define equivalent Euler characteristics for compact Lie groups. Yes, it does. Yeah. but time, or you have 24 hours times 7 per week. So yeah, but it could very well make sense. Yes.
Thank you. Any other questions? We thank the speaker again.